In the last module, we saw a kind of property called safety property. Safety properties were useful to say that something bad does not happen. In this module, we will see what are called liveness properties. As I said, a safety property ensures that something bad never happens. In particular, for a safety property, there is a set of bad prefixes that it avoids. A liveness property comes with a different flavor. A liveness property says that something good happens infinitely often. Here, for example, the good is the green state. The liveness says that the green state appears infinitely often. We will see examples. Let us see how do we specify liveness properties first. When we say GP, that means P should be always true. This is always P. When we say FP, sometime during the execution, P is true. How do we say infinitely often something is true? Not necessarily everywhere, but not just once, but infinitely often like this. To specify a property like that, you can combine GF to say GFP. This just says that in every state, there is a possibility of going to P. So see, FP says that from the initial state, sometime you reach P. GFP says that from every state, FP is true. That means from every state, there is a future state where P is true. That means infinitely often P. So here FP is true, here FP is true because of this, here FP is true because of the state itself, here FP is true because of this state, here FP is true because of this state, and so on. How do we use GF? Let us now finally recall the dining philosopher's problem with which we started in module 1. We had philosophers and sticks. A philosopher can eat only if he has access to both the sticks on his sides. The question was, what should the protocol be so that every philosopher can eat infinitely often? This is the question with which we started with. We saw an example of a protocol. We wrote the protocol in new SMV. If you remember, we had a deadlock scenario. From the initial state where every philosopher is in think state, there was a situation where each of them went to the have left. Let me recall the transition system representing philosopher. Initially, philosopher is in the think state. At some point, he can non-deterministically choose to go either left or right. That means he can either request for the left stick or he can make a request for the right stick. If he is here, that means if he has requested for the left stick, and if indeed the left stick is free, then he can have the left stick. In the process, he makes an assignment saying that I have the left stick. That means sticks of I is equal to philosopher's number I. If he has the left stick, he waits for the right stick, and if the right stick is free, he can go to the eat state. In the process, he sets that the right stick is in my possession. This is a symmetric path. He can eat as long as he wants. And then when he is about to return, he goes to the return state. From the return state, he has to go back to think. In the process, he sets both the sticks to be free. The problem with this protocol was it could lead to a deadlock scenario where all of them are having the left stick and waiting for the right stick forever. We identified this deadlock scenario by forcefully simulating certain paths, but in general, given a transition system, what properties should be checked in order to reveal the deadlock? Here we will make use of liveness. We will check if infinitely often each of the philosophers can eat. Let us see what happens when we check this condition on this model. Here is the philosopher demo.smv, which implements the philosopher transition system that we saw in the slides. These are the locations. These are the transition edges. And in the main, we are calling 4 philosophers using the keyword process. We saw this code in module 1. Let us now try to check the property if infinitely often each of the philosophers can eat. New SMV. So the specification would be check LTL spec GF philosopher 0 dot location equal to eat and GF philosopher 1 dot location equal to eat, and same for the other 2 philosophers. And finally, let us now check the specification. It says that the specification is false. There is an execution where the philosophers do not get to eat infinitely often. Let us have a look at the counter example. This is the initial state. Now in state 2, so there is a loop here. State 2 is the same state, but that is because the process selected is the main process. This is a counter example where the philosopher processes are not even scheduled. This is a counter example due to the main process being scheduled. This is not a satisfactory counter example because the scheduler is being unfair. It is not even scheduling the philosophers. We can try to get rid of such counter examples by adding the following keyword that I'm going to say. So here is the code. We want every philosopher to be scheduled infinitely often. It should not be the case that the scheduler doesn't give the philosopher a chance to take the next step. Such a situation where the philosopher is not even given a chance, rather in general the process is not even given a chance, is called starvation. We do not want to starve a process, so we will add in the module this statement saying fairness running. When we say fairness running, the module which contains this keyword is scheduled infinitely often. Let us see the effect of this. So, still, there is a counter example to this property. Let us see what the counter example is. It says that initially all of them are thinking and the sticks are free. Now the philosopher process 0 is selected and he goes to request, right? Then philosopher 1 is selected. Let us first just look at the locations. So philosopher 0 goes to have, right? Then philosopher 1 requests, right? He goes to have, right? Philosopher 2 requests, right? Then philosopher 2 goes to the have, right? Philosopher 3 requests, right? And then a loop starts where philosopher 3 has, right? And then there is no change in the state. So there are multiple loop starts here. You should see the one in the topmost. The first place where loop starts here is the beginning of the loop. Now all the philosophers are in the have right situation. Let's see what is there inside the loop. All the processes are being scheduled in the loop. Philosopher 0, 3, 2, 1, etc. But there is no change in the state. This is exactly what we wanted. A situation where all the philosophers go to the have right state and all of them are being scheduled. So the scheduler is being fair and still there is no change in the state. This is representing a deadlock. And how did we detect this? We gave the property, is it possible for the philosophers to eat infinitely often? So here eating is the good part and we ask if this good thing can happen infinitely often. In the case of processes, execution or going to the critical section would be the good part and we would want to ask if the process can go to the critical section infinitely often. And this model does not let the philosophers eat infinitely often because of this counter example here where everyone goes to have, right? And then there cannot be any change in the state. This is the kind of counter example that we wanted. Let me summarize the part about the counter example which we saw. The first counter example that we saw was due to only the main process being scheduled, and this is not a fair scheduler. We should add fairness running in the philosopher module. So each time the module is instantiated, the variable or the process that instantiates this module will be scheduled infinitely often. After doing this, we got a counter example which was actually due to a problem with the model and not because of a problem with the main process being scheduled in an unfair manner. We saw a new SMV demo of this. Let us now see another solution to the dining philosopher's problem where this deadlock can be avoided. So here is the scenario. We want to prevent the scenario where each philosopher has one stick. How do we prevent this? Initially, Stick S0 can be accessed by the philosopher to its right, stick 1 by the philosopher to its left, which is 2, stick 3 by the philosopher to its right, stick 2 by the philosopher to its right, which is 2, and finally stick 3 by the philosopher to its left, which is 0. What does this allow? This allows philosopher 0 and philosopher 2 to eat. After they eat, they set the availability of stick 0 to 1, availability of stick 1 again to 1, stick 2 to 3, and stick 3 to 3. This is the scenario. So essentially, stick 0 is initially available to its right and then available to its left. In an alternate way, stick 1 is initially available to its left and then available to its right, and so on. So once philosopher 1 and 3 finish eating, the sticks accessibility are changed. Stick 0 is with philosopher 1 now. What he does is he makes stick 0 available to philosopher 0. Stick 1 is also available to philosopher 1. He sets the availability of stick 1 to 2, and so on. This can be continued, and alternately philosopher 2 and 0 and 2 and 1 and 3 can keep eating. This will avoid a deadlock scenario. We can see a demo of this in new SMV now. So here is the modified code for this new solution. Let me explain the modifications. Firstly, the array sticks can take only 0, 1, 2, 3. It cannot take the word free. The initial allocation of the 0th stick is with process 0. The first stick goes to 2, the second stick goes to 2, and the third stick goes to 0. This is along the same lines as here. Initially, sticks 0 is with 0, 1 is with 2, 2 is with 2, and 3 is with 0. How do we change it in the next transitions? There are some changes as I will describe now. First of all, if the philosopher is in his request left location, he can have the left stick only if the left stick takes the value I. In the previous case, we had said free. Now it will be I. Similarly, he can have the right stick only if the value of the right is I. Now these are the changes here. Now how does the left stick change once he returns the stick? Look at philosopher 2 for instance. Initially he has possession to the left stick and the right stick. The left stick is S2 and the right stick is S1. After he eats, he should pass the left stick to P3 and the right stick to P1. We get this. Once he wants to return, the left stick is made I plus 1 and the right stick is made I minus 1. Just for the special case when I equal to 3, for I equal to 3, his left stick is S3. So once he is done with S3, his left stick should go to 0, not 3 plus 1. It's 3 plus 1 modulo 4. So that is why we have this statement. If it is the philosopher 3 who is returning, then he should return the stick to 0. Similarly, the right stick goes to I minus 1 on return. So this should be return. Just in the particular case when I is 0, then the right stick goes to 3. This is similar to this scenario. This is the changed philosopher according to the second solution. We already have the fairness running here. So we want to see that if the philosophers are executed infinitely often, will they get to eat infinitely often? Let us check this. So here is the specification. From the slides, we would expect that the specification is true. Let us check this. However, it says that the specification is false. That means there is an execution where the philosophers do not get to eat infinitely often. Let us now check it and see what is the thing that is going wrong. Initially, all of them are thinking. Then, philosopher 1 goes to request right. Philosopher 3 goes to request right. And then a loop starts. There is no change in state. That means some philosophers are still thinking. Why does this happen like this? If you remember, we had this possibility. If a philosopher is in think, he can non-deterministically choose to either think or request left or request right. No one is prohibiting him from just staying in the think state. Similarly, if a philosopher is in the eat state, he can continue eating. We want to avoid the scenarios where the philosopher keeps thinking infinitely often or eating infinitely often. In the sense, he keeps taking this transition always from eat to eat or from think to think. This we can specify by saying that fairness, it's not the case that location equal to eat, and fairness, it's not the case that location equal to think. This will reduce all the executions where the philosopher does not keep thinking infinitely often. In the sense, he does not keep staying in the think state forever, and similarly, he does not keep staying in the eat state forever. Fairness not of location equal to eat means, let us look at the executions where the location is not equal to eat infinitely often. Let us look at the executions where the location is not equal to think infinitely often. That means we are looking at executions where the phase where the philosopher is thinking or eating is finite. Let us now check the same specification on this modified code. Here we are. Let's check the specification of the modified code, and new SMV says that the specification is true. So along all paths where the philosopher doesn't get stuck in the eat and the think state, this specification is indeed true. So if you do not allow them to do these unrealistic things, the specification holds and there is no deadlock. So this solution is deadlock free. Let us now summarize this module. We introduced what are called liveness properties, where you can check if something good happens infinitely often. While doing this, we need to take care of fair executions. We do not want to take care of executions where the process is not being scheduled at all, or the process stays in some state infinitely often just because of the way the transitions are modeled. If you remember, from think, we had a possibility of staying in think. So it should not be this case which is creating problems. Hence, we gave fairness running and fairness not of location equal to eat and fairness not of location equal to think. This reduced the executions to realistic scenarios where the processes are being scheduled and they do not keep staying in their critical sections forever.